Welcome to lecture 28. In this lecture, we will discuss about parallel operation of synchronous generator. Let's first see why parallel operation is necessary and how it is done. Let's say that I have two synchronous generators. One has a rating of say 125 megawatt and I have another synchronous generator. It has a rating of 50 megawatt and I have a load of 150 megawatt. Now, if I combine these two, the generation is more than the load, so these two can supply this. But neither this one can alone supply this, nor this one can alone supply this. So what I have to do, I have to connect these two in parallel and then I have to connect it to this load. Now when I do this, it is well understood that these two in combination can supply this, but how much share of this 150 will be supplied by this generator, say call it as generator 1, and how much will be supplied by this two, generator 2, is the point of discussion today. For example, if the load is equally distributed in these two generators, then this one will supply 75 megawatt and this one will supply 75 megawatt. You can see that this is underloaded and this is overloaded. So this is not a good option. So we have to control, if it is connected to a load, we need to control the amount of power that this generator should supply and the amount of generator power that this generator should supply. So it should not be a equal division necessarily. It can be a equal division, but always equal division is not desirable. So in this lecture we will understand how the loads are divided in these two generators. Now for doing this we need to know one thing that is called a governor. This is a part of the turbine that drives the synchronous machine. This is not a part of the electrical machine, but it is a part of the turbine that rotates the machine. Now what does the governor do? The simplest way to answer this is that it controls the speed of the turbine. Now, the governor can be designed such that the speed of the turbine will remain constant whatever load you put. That is, on this axis if you put speed and on this if you put load, you can design a turbine which can have a speed characteristics like this. That is, whatever load you put, the speed will remain constant. This is one type of governor. There can be another design in which if you put load on the machine, the turbine speed will reduce a bit. That is, the speed will not remain constant, but it will reduce. Say at no load this is the speed, say omega 1, and at full load it omega 2. So the speed of the governor do not remain constant. When I say governor or turbine, I want to mean that the machine is simultaneously rotating. So the speed at which the turbine is rotating is not constant, but it drops a bit from the no load to the full load uh, condition. And this type of characteristics of the governor is known as droop characteristics. This is known as DROOP, droop characteristics. This characteristics is known as isosynchronous characteristics. It is used where you have isolated generator, only one generator, so you want that the speed should remain constant, you use this. But when you want to connect more than one generator in parallel, you want a characteristics like that. That is, the speed should reduce with the load. Now, what is the importance of this? Or why we want that the speed should reduce with load? By our understanding, we want the frequency to remain constant, so this will have been a better choice, but we are saying that we want this. Let's understand how these droop characteristics help us in sharing the load. Now we will understand it through a numerical, but before we go to that, let's understand what are the terminologies that we will use. If we have a characteristics like this frequency, that is the frequency at no load, we will call it as the no load frequency, or we will write it as F0. The slope of this is called the droop characteristics, or we will write it like we will call it as delta F by delta P. It will be said something like 2 hertz from no load to full load. It means that the drop from this point to this point is 2 hertz, and the variation of the load here is 0, here it is full load. So here it is 0 load, here it is full load, and the speed here is omega 1, the speed here is omega 2. So we will specify it by two things. One is the no load frequency, another is the droop characteristics. Now we will say that whatever we have discussed till now is regarding a synchronous generator. Now if we don't remember this part, if we totally forget whatever we have discussed here, we can take this one as a simple numerical of a straight line that we have learned in our class 11th. So you can say that this is the intercept, from here to here is the intercept, this is the slope, here we have a variable on y, here we have a variable on x. So how we write the equation of this? Y is equal to mx plus c. Now we will use this knowledge of straight line to solve this. So though we have started with parallel operation of synchronous generator, what we will essentially solve is a numerical of a straight line that we have learnt in class 11. Now one thing you need to understand is that what is the slope of this line? It's negative because this angle is obtuse angle, so tan of this angle is negative. So the slope here will be negative. So here in this droop characteristics, the slope is negative. Let's take a numerical and try to understand how this knowledge of straight line can help us in solving a problem on parallel operation of synchronous generator. This is quite a big numerical. Big means there is a lot of things that is written here. You can read it at your convenience. So let me just quickly say what is there in this. There are three generators that are there. Generator A, B and C. There are three generators. Generator A, this is generator A, this is generator B and this is generator C. These are three generators. Now what has been said? It has been said that the droop characteristics is given. One is that its rated power is given 50 megawatt and the droop characteristics is given. So for this generator, then it has been mentioned that they combine, in a combined way they are supplying 80 megawatt, and under this condition generator A and B is supplying 20 megawatt each. So what does it mean? It means that power from generator A plus power from generator B plus power from generator C is 80 megawatt, and out of this is 20 plus this is 20, so power generated by generator C is 40 megawatt. So this is what is being said here. Now the first question is to calculate the no load frequency of the three generators. Let's see how to do that. Now what we said is that these three generators are connected together in parallel, and together they are supplying a load of 80 megawatt. Out of this, it has been said that this is 20 megawatt, this is 20 megawatt, so of course this will be 40 megawatt. And it is being said that since they are connected in parallel, all of them should have same frequency, so it is operating at 50 hertz. It is being said that it is operating at 50 hertz. Now the question is, what is the no load frequency of the 3 generator? Calculate the no load frequency of the 3 generator. Let's see one of the case. What is being said is that you have a group characteristics like this. It has been said that I am talking about generator A. It is supplying a power of 20. So this power is 20 megawatt. And it is operating at a frequency of 50 hertz. We also know that the slope of this line, it has been mentioned here, the generator A has a drop in frequency from no load to full load to be 2 hertz. So what does it mean? It means that the slope of this line is minus 2 hertz from no load to full load, that is per 50 megawatt. So what is being said? Let's see this one again. Drop in frequency from no load to full load is 2 hertz. It means that, say this is your no load condition, this is your full load condition. So from no load to full load there is a drop in of 2 hertz. So what is the slope? The slope is delta F by delta P. Delta F is 2 hertz, delta P is 50 megawatt. Why 50 megawatt? Because the full load capacity of the generator is given to be 50 megawatt. Now let's write a straight line equation. So on this axis we have F, on this axis we have P. So we can write F is equal to, okay, I'll write like this, y equal to mx plus c. What is y here? Y is F. What is m here? M is minus 2 by 50 into x. X is p plus c. Now it is being said that it is operating at 50 hertz. So put here 50. This will be minus 2 by 50 into 20. Why 20? Because my generator 1 is supplying 20 megawatt plus C. Here you have to find C. So what will be C? C will be 50 plus 4 by 5, that is 50.8. So if you look at the other part of this numerical, that is calculate the no load frequency of 3 generators. So I have calculated for generator 1. So for generator 2 it will be again a straight line problem. For generator 3 it will be again a similar straight line problem. The next part is that if the load is increased to 100 megawatt, calculate the load sharing and the bus frequency. It will again be a straight line problem. But understand that when you increase the load, the generator 1 and generator 2 will no longer supply 20 megawatt. Their share will also increase. So try to solve this two part from here and one part from here and submit it as an assignment. I will again solve it after 2-3 classes, but I hope that it is quite straightforward and you will be able to do it. Don't solve it as a synchronous machine problem. Take it as a straight line problem from class 11 and solve it. Thank you.